Hi everyone. So today let's have a look at how to implement Boolean function with PLA. Do you remember what was PLA? Um, it's a type of combinational programmable logic device. So it has a programmable AND array and a programmable OR array. This is a typical structure of a PLA diagram. It has an input. So in this case, it has three inputs and outputs. So here we have two outputs. K product terms means K AND gates. So here we have four AND gates and sum terms. So I have two OR gates. And also I have two XOR gates. And all this little blue cross mark means there is a connection. Where there is no cross mark, it means there is no connection. So with that being told, what would be the Boolean expression for F1 and F2? Let's have a look together. So first, each input goes through a buffer invert combination. So here we have input A, and it goes through a not A, which is the line on top, and then the variable A, which is the line on the bottom. Here is our programmable AND array, programmable OR array, and for each output variable, we have XOR gate for true or complement. So for the Boolean expression, we need to evaluate each term one by one. So after the programmable AND array, we get A, B prime, which is the output of the first AND gate. Second output is, this is C, this is A, so the output of the second AND gate is AC. The output of the third AND gate is, this is B, this is C, so this is BC. And the output of the fourth AND gate is A prime, B, C prime. So the first OR gate, the value here is, let's see, AC or BC. And this line, we have three terms. So AB prime or AC or A prime, B, C prime, B, C prime. But this is not F1, F2 yet, because F1, we are having this Boolean expression X or 0. So here we have F1 equals AB prime or AC or A prime, B, C prime, X or 0. And if we expand XOR, we get this Boolean expression. So it's AB prime or AC or A prime, B, C prime, prime, and 0 or the Boolean expression and 0 prime. So 0 prime, this is what? So the first term, this is 0 because anything and 0 is 0. And the second term, this 0 prime is 1. So eventually we get F1 equals AB prime or AC or A prime BC prime. So here we can know that an expression X or 0 is still itself. It didn't change the value on the other side of the XOR gate. How about F2? So F2 is a AC or BC XOR 1. Here, if we expand this expression, we have AC or BC prime and 1, or AC or BC and 1 prime. So this first term is AC or BC prime. The second term, 1 prime is 0, so the whole thing here is 0. So this whole term equals 0. Eventually, we have only AC or BC prime. So an expression x or 1 is complement. This is a Boolean expression for F1 and F2. And with the Boolean expression, we can write a PLA programming table. PLA programming table. So here we have three sections. The first section is the product term. Um, let's have a look at how many product terms inside a F1 and F2. So we have AB prime, AC, A prime, B, C prime. And F2 here also have AC and BC. So there are four different product terms in these two Boolean expressions. So the first section is we write all the different product terms and label them one, two, three, four. The order doesn't really matter here. Uh, and then we have an input section, which is the input of all our AND gates. So we have AB prime. Here, 1 means the true value of a variable A. 0 means the complement or the prime of the variable B. And then a dash means there's no connection with C. So C, you can think of it as don't care condition or it doesn't matter. So when we are labeling the cross mark on our PLA diagram, we don't need to label anything on C. Then we have AC, which is 1-1 because B is not in this expression. And then BC dash 1, and A prime, B, C prime. So whenever there's a prime, we use 0, so it becomes 0, 1, 0. The third section is a OR gate. So here are all the outputs. If it's in its true form, then we just write parentheses T. So F1 is AB prime. If it's in the Boolean expression, we use 1. If it's not in the Boolean expression, we just use a dash. So F1 is AB prime or AC or A prime B C prime. And F2 is AC or BC, but it's in the complement form. So here we have a parenthesis and then a complement. When we are drawing the connection on the PLA diagram, if it's complement, we need to X or 1 using this Boolean expression. So F2 has AC or BC. So AC, BC is 1, the other two are dash. And here we have a parenthesis, C meaning it's a complement form. So basically with a PLA diagram, you can write the Boolean expression and then you can also write the PLA programming table. For if given a programming table, you are also able to write the or draw the PLA diagram and write the Boolean expression. Okay, so those are some basic elements we need to use to implement the Boolean function with PLA. Next, let's have a look at an example. So implementing Boolean function with PLA has the following three steps. Step 1 is simplify the Boolean function using Kmap. Step 2 is write down the PLA programming table. Step 3 is draw the connection on the fuse map. So the PLA diagram, that is also called a fuse map. Let's have a look at this example. We have two Boolean expression. F1 is sigma 0, 1, 2, 4. F2 is sigma 0, 5, 6, 7. Step 1 is we need to simplify the Boolean expression using Kmap. So here is a Kmap for F1. We have 0, 1, 2, 4. So 0, 1, 2, and 4. 0, 0, 1, 2, and 4. So here is a technique to help us find the smallest number of total product terms. So for each Boolean expression, we write it in two forms. The first one is F1 equals, just normally we just circle all the pair of ones. And then we get three product term. So this is A prime B prime or A prime C prime or B prime C prime. Another way is we can circle all the zeros. So here is a zero and then get its complement form. So here we have three groups of zeros, but F1 is the complement of these three groups. So we get AB or AC or BC, and then there's a big prime on the outside. And F2 is the same. We get two Boolean expressions. So to do this, we can compare these four Boolean expressions. We can get the minimum number of product terms. So if we can find minimum number of product term, it helps us to simplify our PLA connection diagram. So after observation, we found that if we use the second form for F1 and the first form for F2, we have the smallest number of um, product terms. So they both have AB, AC, and then F1 has BC, F2 have A prime, B prime, C prime. So totally there are four product terms. We next we need to write the PLA programming table. So here are all the product terms. And the input is A, B, C, three variables. And AB is 1, 1, because C is not in the Boolean expression, so C is a dash. And then AC is 1, B is not in the Boolean expression, so B is dash, and then C is 1. BC is dash 1, 1, A prime, B prime, C prime. Because they are all prime, so we use 0 to represent it. And then F1, we are using the complement form, so we have parentheses, C means it's a complement form, and then A, B, A, C, B, C. A here is A, B, A, C, and then B, C. F2 is its true form, so it has A, B, A, C, A prime, B prime, C prime. So A, B, A, C, A prime, B prime, C prime. Next, we need to draw the PLA diagram. So basically, you just need to draw the cross mark on all these dots. There's a circle means you can draw a cross mark there. So first we have, let's see, we have AB, AC, and BC. So this is AB. The output of the first one is AB, and then AC. This is the output of the second AND gate. BC. This is a B. This is C. So the output of the third AND gate. And then A prime, B prime, C prime. So this is A prime, B prime, C prime. So here it draws a separate NOT gate. It's the same as the symbol we saw previously in here. So one is true, one is not. Whenever there's a bubble, it means not. And then F1 equals, let's see, AB or AC or BC, but with a prime. So whenever I need to have a prime, we need to XOR 1. So an expression XOR 1 is this. So F1 is AB or AC or BC prime. So because we want to get the complement of F1, we need to put a cross mark at here, XOR 1. So an expression XOR 1, we can get its complement. So but this wire here is connecting to AC, BC, AB, AC, and BC. For F2, because it's true form, so we just use XOR 0. And here is AB, AC, and A prime, B prime, C prime. So we just draw the cross mark at the corresponding output location. So this is the PLA diagram. And this way we have implemented these two Boolean functions with a PLA. Here is another example. So try it yourself. And then first we have Boolean expression and then use Kmac to simplify this Boolean expression. I give you some reference example solutions here. So uh, you can try it yourself. F1, I think these two can give the minimum number of product terms. So here is my PLA programming table. And then I didn't finish. Oh, so we have BC, which is cross market BC, and then AB, A prime, B prime. F1 is my Boolean expression for F1 is BC or AB, and then F2 is A prime, B prime, or BC prime. So this is a BC, AB. F1 is its true form, so we XOR 0 with it, and then F2 is BC AB prime. So BC A prime B prime. And then it's complement form, so we are XORing 1 with it. This is implementing the Boolean expression with PLA.